Okay, hello! So in today's video, we're going to be taking a look at improper integrals. What does that mean? Well, we're gonna find out. Let's look into it right now. So improper integrals are defined as integrals where one or both of the limits of integration are infinity or negative infinity. We've been dealing with limits that are constant numbers and numbers that we're familiar with, but hey, why couldn't they be infinity or negative infinity? Well, they can. So we need to learn how to solve those types of integrals. So we can use limits to change the limits of integration to be definite, right? So the idea is that if we have a function that's continuous on the interval a to infinity, then the integral from a to infinity of f of x dx is going to be equal to the limit as b approaches infinity of the integral from a to b of f of x dx. So all we did was we took out that infinity sign, replaced it with a different variable, let's call it b for now, and then took the limit as b approaches infinity of that integral there. That's all we're doing here. And this integral is now solvable as normal. We compute the integral of f of x, and then we use the fundamental theorem of calculus, where our limits are a and b. And we'll just treat b as a variable when we do the fundamental theorem of calculus. We won't have a number to plug in for b, but we'll just put b in for x in this case. So we'll see that in an example. Similarly, if we have the interval from negative infinity to b, then the integral from negative infinity to b of f of x is equal to the limit as a approaches negative infinity of that integral there. So a similar idea where we take away that negative infinity sign, replace it with the variable, and take the limit as that variable approaches negative infinity in this case, because that's the value we replaced with a. Finally, if both of our limits are bad, negative infinity and infinity, our idea is we'll split up the integral into the sum of two integrals, right? Recall that if we're on the interval a to b and c is in the interval, then the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So this will be the technique that we use when we see that the bottom limit is negative infinity and the top limit is infinity. We'll split it up into the sum of two integrals where c is any real number. Choose whatever suits you best. And then compute these integrals individually. And to do that, we may have to use one of these above two techniques because we still have one of the limits being a form of infinity. Finally, we say an integral converges if the integral equates to a finite value, and an integral diverges if it equals infinity or cannot be determined. Infinity or negative infinity, something like that. So those are the vocabulary that we will be using. So let's see an example using improper integrals. We want to evaluate the integral from 1 to infinity of 1 over x dx. We see an infinity as the upper limit, so what we'll do is we'll do that variable replacement, where we put a as our upper limit, but we take the limit as a approaches infinity of our integral. Now this integral makes us happy because the limits are nice to work with, and we can solve this as a normal definite integral. We know that the integral of 1 over x is ln of x, so that's what we see here, and our limits go from a down to 1. All the while we have this limit as a approaches infinity still lingering with us, which we'll take care of soon. Now we'll use the fundamental theorem of calculus, plug in our a, plug in our 1, and now we handle the limit as a approaches infinity. We can plug in infinity for a, and we say that this is equal to the natural log of infinity minus the natural log of 1, which is equal to infinity. Hence we say the integral diverges. So that's one example. Let's try to do an example from scratch. So here we see the integral from negative infinity to 0 of e to the x dx. So I see that my bottom limit isn't particularly great, so we want to do a variable replacement with that. I like to use the letter A just because it's the first letter of the English alphabet. So what we'll do is we're going to replace this with the limit as a approaches negative infinity, because that's the value we're replacing, of the integral from with the bottom limit a, top limit 0, of e to the x dx. Okay, so now we can evaluate this definite integral. It's just that we have a variable as our bottom limit, but that's not that big of an issue. So we'll say that this is equal to the limit as a approaches negative infinity. Well, the integral of e to the x is just e to the x, and this will be evaluated from 0 down to a. Okay, so this is going to be equal to the limit as a approaches negative infinity of e to the 0 minus e to the a. E to the 0 is simply just 1, so we can put a 1 there. And now we can consider the limit. So suppose we plug in negative infinity for a, we get this is equal to 1 minus e to the negative infinity, which is equal to 1 minus 1 over e to the infinity. We have 1 over a massive denominator, so that second term is going to be equal to 0. So this equals 1 minus 0, which is equal to 1. And that's our answer. So a pretty simple example, but we're starting to see a pattern emerge where we replace one of or two of the limits of integration with a variable, and then take the limit as that variable approaches infinity, negative infinity, and go from there. Let's do some more examples. So here we see the integral from 0 to infinity of 1 over x squared plus 1 dx. The integral already looks really nice, 1 over x squared. We should already know what that integral is equivalent to, but we need to manage our limits first. So we see the upper limit isn't ideal, so we'll replace that with a variable. We'll choose a again. So this is going to be equal to the limit as a approaches infinity of the integral from 0 to a of 1 over x squared plus 1 dx. The integral of x squared plus 1 is inverse tangent of x, or arctangent. So we'll use arctangent. So arctangent of x, and it's evaluated from a down to 0. So now we can do our fundamental theorem of calculus. So this is the limit as a approaches infinity of arctangent of a minus arctangent of 0. Let's suppose we plug in a equals infinity to here, then we get arctangent of infinity minus arctangent of 0. Both of these have numeric values to them. Arctangent of infinity might be a little bit tough to remember. There's a couple ways of thinking about it. First, you can think about the graph, and remember that the graph of arctangent is sort of like a normal tangent graph, just like rotated a bit, so it looks like this, and there's actually a horizontal tangent line here. Another way of thinking about it is arctangent is inverse tangent, so I would think tangent of what angle yields infinity? Well, tangent of theta is equal to sine of theta over cosine of theta, and if I want tangent of theta to reach infinity or become a really large number, that means I want my denominator to be as small as possible. So essentially I want cosine of theta to be equal to 0, and that occurs when theta equals pi over 2. So arctangent of infinity is pi over 2, and that's actually where our horizontal asymptote is on our arctangent graph. There's also another horizontal asymptote down here at negative pi over 2, but note that we're using positive pi over 2 because we're going towards positive infinity. Arctangent of 0 is simply equal to 0, so this equates to pi over 2, and that's our answer. Another simple example, but very similar to the previous problems we saw, so hopefully you're starting to feel comfortable with this. By the way, we can also say that since the integral equals pi over 2, which is finite, we can conclude that this converges, the integral converges. Same with the previous problem, since it equals 1, which is finite, it converges as well. Let's do another problem. Another integral, 1 to infinity of 1 minus x times e to the negative x dx. We see the infinity, we're going to have to do that variable replacement. So we can say that this integral is equal to, let's use a different color. Yeah, I'm feeling this color. Limit as a approaches infinity of 1 to a 1 minus x e to the negative x dx. And now we just have to evaluate that integral as normal. I'm actually going to move this down here. So how are we going to evaluate this integral? It's not a simple one, so we can start to think of which techniques we'll use. We could use u substitution, maybe, but what will we choose as u? Maybe like e to the negative x, but that won't really do anything because there's nothing to cancel with, so that's not going to do it. Some of the advanced trig techniques don't seem to work here. Integration by parts could work. That's definitely a viable option, but maybe there's one that's even quicker. So I hope you've seen our video on tabular integration, because that's the technique we're going to be using here. Let's do some tabular integration. So the way that works, recall, is we choose a u and we choose a dv, and we choose them in a way such that we continuously take the derivative of u until we reach 0, and continuously take the derivative of dv. So we want to choose a u whose derivatives will eventually reach 0. So in this case, I'm thinking 1 minus x would be a good choice for u, which means dv would be e to the negative x. The derivative of 1 minus x is negative 1, and the derivative of negative 1 is 0, so we've reached 0, we're in good shape. The integral of e to the negative x, you can solve that on your own. You could use u substitution to solve that, but this I think is worthwhile to just memorize. This is equal to negative e to the negative x, and similarly I encourage you to memorize the integral of negative e to the negative x is equal to e to the negative x. So we've created our chart. The next step is to draw our arrows as such, and then we alternate between multiplying by positive 1 and negative 1. So the first one is positive 1, second one is negative 1. So the limit, or the integral, equates to, I'll put it in brackets here, we do 1 minus x times positive 1 times negative e to the negative x, so just multiplying with the values along that arrow, and then we add to that the product of the values along the second arrow, which is negative 1 times negative 1 times e to the negative x. And remember, this is being evaluated from a down to 1. So let's clean up the stuff inside of the brackets. So this is equal to the limit as a approaches infinity of this positive 1 term we don't really care about. So let's distribute this negative e to the negative x into these two terms. So negative e to the negative x times 1 is negative e to the negative x. Negative e to the negative x times negative x would be positive x e to the negative x. Then we add to that negative 1 times e to the negative x, which is just e to the negative x. We see that the first and third terms will cancel. So we're simply left with, and don't forget our limits going from a down to 1. So this is equal to the limit as a approaches infinity of x e to the negative x evaluated from a down to 1. So let's now plug in our limits using the fundamental theorem of calculus. So that's the limit as a approaches infinity of a e to the negative a minus 1 times e to the negative 1, which we can rewrite as just 1 over e. Okay, but what is the limit as a approaches infinity of a e to the negative a? So let's handle that separately. The limit as a approaches infinity of a e to the negative a, let's just see what happens when we plug in infinity for a. That will be equal to infinity times e to the negative infinity, which is equal to infinity times 1 over e to the infinity, which is infinity over infinity. That means we have to use L'Hopital's rule. So let's just move this off to the side, and we can say that the limit as a approaches infinity of a e to the negative a, which I'm going to now rewrite as a over e to the a, which is an equivalent form, but since we know we have to use L'Hopital's rule, we need a numerator and denominator. This is equal to the limit as a approaches infinity of the derivative with respect to a of the numerator divided by the derivative with respect to a of the denominator, which is equal to the limit as a approaches infinity of 1 over derivative of e to the a is e to the a Now when we plug in infinity for a, we get 1 over e to the infinity, which is equal to 0. So that means our integral from 1 to infinity of 1 minus x e to the negative x dx, we concluded that this was equal to the limit as a approaches infinity of a e to the negative a minus 1 over e, but we said that this limit was equal to 0, but we subtract away our 1 over e, and our answer is negative 1 over e. So there you go, another example, this time with some L'Hopital thrown in there. So really what we're doing is we're just taking an integral and simplifying it to a limit. Simplify if you think limits are simpler than integrals, but I think these limits are easier to solve than something like this, right? That just seems terrifying. So there we go. Let's do another one. Okay, so here we see an example of an integral where the bottom limit is negative infinity and the top limit is infinity. As we saw in the opening slides to this presentation, the way we would solve this is to split it into the sum of two integrals where the sum is based off of a breaking point which is within the range, any real number. I like 0 since it's easy to work with, so that's where I'm going to split this integral up. So we're going to say this integral equals the integral from negative infinity to 0 of the same integrand plus the integral from 0 to infinity of the same integrand. And now we can solve both of these integrals individually, right? That's just, as we've seen in previous examples, where one limit is bad, it's just now we have to do it twice and take their sum. So we should be feeling a little bit better about that. Let's just write it in terms of the limits, what we're looking for. So we can say that this is equal to, I'm actually going to write it over here. So for the first one, we can take the limit as a approaches negative infinity of the integral from a to 0 of e to the x over 1 plus e to the 2x dx. And for the second one, we'll use another limit, but let's use a different variable just so we're not getting confused. And this is the limit as b goes to infinity of the integral from 0 to b e to the x over 1 plus e to the 2x dx. Notice how we're actually going to be solving the same integral here. It's just the limits that are changing. Limits being the limits of integration, but also the limit on the outside. So let's just handle the integral on its own, and then we'll take care of all of the limits later. So in red, we'll do the integral of e to the x over 1 plus e to the 2x dx. Okay, so it's not immediately obvious what we could do. U substitution seems really tempting here with that denominator, but if we try it by letting u equal 1 plus e to the 2x, then du will be equal to 2e to the 2x, and it's not quite there because that e to the 2x doesn't really cancel with this e to the x. So u substitution doesn't immediately work. Keyword being immediately. But what if I rewrote this as e to the x over 1 plus e to the x squared dx? Now maybe we're feeling a little bit better. That denominator has arctangent vibes to it, where it's like 1 plus something squared. So let's see what we can do with that. What if we try u substitution again, but now we use u equal to e to the x, because we see a lot of e to the x is surely something should cancel. So we'll let u equal e to the x, which means du equals e to the x dx. That means our integral is u divided by, let me use green for where I use u, divided by 1 plus, we can write u squared in the denominator, times du over e to the x. But now we don't have an e to the x to cancel with. But we do. It's just that we changed the numerator from being e to the x to u. So let's just leave the numerator as e to the x, and now we see the e to the x's cancel. And we're left with the integral of 1 over 1 plus u squared du Sure enough, our arctangent vibes premonition was correct, because that is the equal to the arctangent of u. And now we substitute e to the x for u. So this is equal to the arctangent of e to the x. Great, so now let's return to our, sum up here with all of the limits. And we can rewrite this as the limit as a approaches negative infinity of, well, now we've solved this integral. So this is going to be arctangent of e to the x evaluated from 0 down to a, plus the limit as b approaches infinity of the arctangent of e to the x evaluated from b down to 0. Okay, so let's fundamental theorem of calculus this. This should be equal to the limit as a approaches negative infinity of arctangent of e to the 0 minus arctangent of e to the a plus the limit as b approaches infinity of arctangent e to the b minus arctangent e to the 0. Let's try substituting in for our variables infinity for a, or negative infinity for a, infinity for b, and see what happens. So this would be equal to the arctangent of e to the 0 minus the arctangent of e to the negative infinity plus arctangent of e to the infinity minus arctangent e to the 0. We see the first and last terms cancel. So we're just left with arctangent of e to the infinity, which is basically just infinity, minus arctangent e to the negative infinity is 1 over e to the infinity, which would be equal to 0. Okay, so now solving for this, arctangent of infinity we've solved for earlier in this video, that's equal to pi over 2. And then arctangent of 0 is going to be equal to 0. So our final answer is pi over 2, and we can say that the integral converges. There we go, another example, just some fun little integration trick there to solve it, but the thing is the same. Split the integral into 2 and then solve those each individually. Okay, so let's do one more. Here we see the upper integral is infinity, so we can change that. So this is going to be the limit as a approaches infinity of the integral from 4 to a of 1 over x ln of x cubed dx. Let's take care of the integral first, so let's just do that off to the side. The integral of 1 over x ln of x cubed dx. And we won't worry about the limits for now, we'll take care of that later. What are we thinking for this? Maybe u substitution. I don't want to let u equal x because then I'll have ln of x left over, so why don't we let u equal ln of x? I don't want to let it equal ln of x cubed because I know I'll have to do the chain rule and I'll still have some ln of x's left over, so let's just let u equal ln of x. That means du equals 1 over x dx. And now we can turn back to our integral and get the integral of 1 over x times u cubed times dx is now equal to x du, and we see that the x in the denominator cancels with the x with the du. We can rewrite this as the integral of u to the negative 3 du, and now this is a simple power rule, negative 1/2 u to the negative 2, which is equal to negative 1 over 2u squared, and now we'll substitute in for u, which we said was equal to ln of x. So that's our integral evaluated. Turning back to the limit, we get the limit as a approaches infinity of negative 1 over 2 ln of x squared evaluated from a down to 4. Fundamental theorem of calculus this to get negative 1 over 2 ln of a squared minus negative 1, so this is going to be plus 1 over 2 ln of 4 squared, and there we go. Now we can try plugging in infinity for a, and we get, let's just rearrange the two terms, so the positive one is first, so this is 1 over 2 ln of 4 squared minus 1 over 2 ln of infinity squared. Ln of infinity is infinity, so the denominator is going to basically be infinity. So that second term goes to 0, and our final answer will be 1 over 2 ln of 4 squared. So nothing too tricky about this one either, just another practice problem, but you can see the pattern is basically the same, which makes this really nice. But wait, there's more. We have to talk about infinite discontinuities. And now things are just starting to seem like complete jargon. What does improper integrals with infinite discontinuities even mean? That sounds like I'm speaking some Martian language, but alas, we have to learn what it means. So if a function has a vertical asymptote at x equals a, then we say that the function has an infinite discontinuity at x equals a. So when we're computing an integral where the function has an infinite discontinuity, we need to use limits to compute that value, just as we did so when we were computing limits of functions with vertical asymptotes. So if f is continuous on some interval a to b, and there's an infinite discontinuity at b, which is the closing part of our interval, then the integral from a to b of f of x dx is going to be equal to the limit as c approaches b from the left, this is b minus, of the integral from a to c of f of x dx. So similar idea to when we saw infinities in our limits, where we replace the bad limit with a new variable and take the limit as that new variable approaches the bad limit. Similarly, if we have this interval and the infinite discontinuity is the left side of the interval, then the integral is equal to the limit as c approaches a from the right-hand side of the integral from c to b of f of x dx. And lastly, if we have an interval a to b and the infinite discontinuity is somewhere in between them, then we will split apart our integral at that discontinuity and evaluate those integrals individually, just like we saw when our limits were negative infinity and infinity. Lastly, for some vocabulary, the improper integral converges if the limit exists, otherwise we say it diverges, similar to before. And in this case right here, where we're taking the sum of two integrals, if either one of them equals infinity, or if either one of them diverges, then we say that the left-hand integral also diverges. Let's see an example of this in action, and then we'll do some for our own. So here we see the integral from 0 to 1 of 1 over the cube root of x. So we'll notice that when x equals 0, our denominator will equal 0, which would indicate that there's a vertical asymptote at x equals 0. And looking at the graph over here, we see that that is true, where this function is curved like this, but as we approach 0, it's growing very quickly, and it approaches infinity. So the way we solve this is we consider the quote-unquote bad limit. In this case, it's the left-hand side of our interval. So we'll take the limit as a approaches 0 from the positive side, from the right side, of the integral from a to 1, so replacing that 0 with our variable, of the same integrand, where I just rewrote this as x to the negative 1/3 power. We can now solve it using the power rule, so we get that, and then we still have our limits here from 1 down to a, fundamental theorem of calculus it, and then we can compute our limit with this, so we plug in this 0 plus for a, considering it from the right-hand side, gradually approaching 0 from the right-hand side, and we can compute this as normal. We get 3/2 minus 0 equals 3/2. So there is an essence of those improper integrals with infinite limits. It's a very similar solving procedure. We just need to be a little bit careful, take that extra step to determine where is our discontinuity. So let's do an example for ourselves. This one is eerily similar to the example we just saw, but that's on purpose, so that way we feel comfortable with what we're doing. So the first thing that might be sticking out to you is the x cubed in the denominator, which would indicate that there's a vertical tangent line where x cubed equals 0. The only solution to that is when x equals 0, so we can say that there's going to be an infinite discontinuity at x equals 0. Notice that our integral has limits 0 to 3, so 0 is the left side of the limit. So if we're doing an integral with an infinite discontinuity, we have to do that variable replacement as we just saw, and we're going to be replacing that 0 limit. So this will be equal to the limit as a approaches 0 from the positive side, since it's the left limit, of the integral from a to 3 of 1 over x cubed dx. And I'm going to rewrite this integrand as x to the negative 3. Because now we can solve this integral as normal, just treat it as a normal definite integral, and we can solve it using the power rule. So we'll keep this limit as a approaches 0 from the positive side. The integral of x to the negative 3 is going to be equal to 1 over negative 2 times x to the negative 2, which we can rewrite as negative 1 over 2x squared, and this is evaluated from 3 down to a. Let's fundamental theorem of calculus this. So this is the limit as a approaches 0 from the positive side of negative 1 over 2 times 3 squared plus 1 over 2 times a squared. So that will be equal to the limit as a approaches 0 from the positive side of 1 over 2a squared minus 1 over 2 times 3 squared is 18. Cool. So now let's consider what happens when we plug in a equals 0. So this would be equal to 1 over 2 times 0 plus squared minus 1 over 18. Our denominator is 0, so we have 1 over 0, which we can conclude is infinity, minus 1 over 18. So we say that our integral is equal to infinity, and it diverges. So we can see how similar it is to some of the problems we saw prior where we didn't have infinite discontinuities, but our limits of integration were forms of infinity, so it's a similar solving experience here. Just again, need to determine where is our infinite discontinuity. So for a brief aside, which is tangential but still incredibly important, what happens if you don't immediately recognize that there's an infinite discontinuity in this problem? What if you just think this is a normal integral problem? Let's do that off to the side. So if we were to just normally take the integral of 1 over x cubed dx, that will be equal to, as we solved, negative 1 over 2x squared, evaluated from 3 down to 0. Fundamental theorem of calculus, you get negative 1 over 18 plus 1 over 2 times 0 squared. When you see that 0 in the denominator, you know that something's a little bit fishy. And sure, maybe you could say that, okay, well that's just equal to negative 1 over 18 plus infinity. But there is an infinite discontinuity there, which is why we're getting that 0 in the denominator. So when we see that, then you should resort back to this way where you properly take the limit as a approaches 0 of the integral and go from there. However, we won't always be bailed out this easily. This worked out nicely when one of our limits was where the infinite discontinuity is, but that isn't always the case. For example, the integral from negative 1 to 2 of 1 over x cubed dx. So we already know that there is an infinite discontinuity because we've seen this integrand here. Let's suppose we didn't know that, and we solve this as normal. And then we'll compare it to what we get when we solve it when we recognize that there is an infinite discontinuity. So the integral of 1 over x cubed is going to be equal to negative 1 over 2x squared, evaluated from 2 down to negative 1. Using the fundamental theorem of calculus, we get negative 1 over 8 plus a half, which is equal to 3/8. So this is our solution just by doing the normal fundamental theorem of calculus. But we recognize that there's an infinite discontinuity at 0. And notice that 0 is in the interval negative 1 to 2, which is where our integral is being computed against. So in that case, we need to split up our integral at that point of discontinuity. So we will say the integral from negative 1 to 2 of 1 over x cubed dx is equal to the integral from negative 1 to 0 of 1 over x cubed dx plus the integral from 0 to 2 of 1 over x cubed dx. Now, we can solve these integrals individually, so I'll do the first one in pink and the second one in blue, I suppose. So for the first one, the integral from -1 to 0, we'll rewrite this as x to the -3rd dx. So though we've already recognized the infinite discontinuity, we haven't properly handled it in our solving procedure. We've just broken it apart into two integrals. Now we have to actually solve these as we normally would, like we did in the previous problem, where we set it a variable and then take the limit. So this will be equal to the limit as a approaches 0 from the left, since 0 is our right limit this time, of the integral from -1 to a of x to the -3rd dx. We've already solved for the integral of x to the -3, so we can say that this is equal to the limit as a approaches 0 from the left of -1 over 2x squared, evaluated from a down to -1. Fundamental theorem of calculus this to get -1 over 2a squared plus 1 over 2 times -1 squared, which we can rewrite as the limit as a approaches 0 from the left of a half minus 1 over 2a squared. Okay, we can plug in this 0, -0 minus for a, and we get that's equal to 1/2 minus 1 over 2 times 0 from the left squared. That denominator will essentially be 0, so it's going to go to -infinity, so this will be 1/2 minus infinity, which is essentially equal to -infinity. At this point, we can basically conclude that this integral will diverge, because we found that one of the integrals it diverges on its own, so that means this sum will also diverge. But just for the sake of practice, let's solve for the other integral as well. So the other integral from 0 to 2 of 1 over x cubed dx is going to be the limit, as we'll call it b this time. It approaches 0 from the right-hand side of the integral from b to 2, x to the -3rd dx. To speed through this a little bit, we get the same result here, evaluated from 2 down to b. This is the limit as b approaches 0, plus of -1/8 plus 1 over 2b squared. Plugging in that 0, we get -1 over 8 plus infinity, which is equal to infinity. So we're essentially saying that our integral -1 to 2 of 1 over x cubed dx is equal to -infinity plus infinity. Can't really conclude anything there, so we have to say that the integral diverges. And notice that this conclusion is different from the 3/8 that we got before. Here we concluded that the integral converges to 3/8, but the actual answer is that it diverges. And the reason is because of that infinite discontinuity at x equals 0. So what's the lesson here? If you see an integral, one of your first thoughts should be, is there a way to make the denominator equal to 0? And if so, handle that infinite discontinuity. Because something like this, it's incredibly easy to get trapped into thinking, oh, that's just a simple definite integral that I can solve using the power rule and, get this answer. But that's wrong. And I've done this so many times where I'm like, oh, this is so easy. But it's not. So be careful, be mindful. Unfortunately, this is just one of those tricky things where you have to be cognizant of the fact that this could occur and notice it and solve it accordingly. Let's do one more example so it sits comfortably with us, and then we'll call it a day. So we have the integral from 0 to infinity of 1 over the square root of x times x plus 1. So as I just said, the first thing we should be thinking is, hey, is there a way for our denominator to be equal to 0? And the answer is yes. If either of these two terms are 0, then our denominator is 0. This first term is equal to 0 when x is equal to 0. The second term equals 0 when x equals -1. However, -1 is not in the interval from 0 to infinity, so we don't really have to worry about that. 0, however, is. So that's something to be aware of. That means we're going to have to use some sort of limit in place for 0. We'll have to do that variable change and then take the limit as a approaches 0 plus of the integral. However, we also have an infinity in our integral, which means we're going to need another limit because we'll have to do a variable replacement for that. So that means we'll need a limit on top of a limit, which seems very complex, and it probably is. However, there's a way to simplify it just a tiny bit. And the way we can do that is, if we know we need two limits, sort of, why don't we just have two integrals and use one limit for both of them? So what I mean for that is one integral should handle the case where the limit is 0, because we know that this limit is bad. And the other integral should handle the case where the limit is infinity, because we know that's also bad. So we can do that by splitting this integral into the sum of two integrals, where we choose a breaking point, and I'll choose the limit, or I'll choose the value of 1 as our breaking point. So this integral on the left is equal to the sum of these two integrals. And we can see this is slightly nicer now, because we can evaluate these two individually, and both will require only one limit. This first integral will only need one limit, because that's the only bad thing about it, and the second integral will only need one limit, because the infinity is the only bad thing about it. So now let's actually incorporate those limits into our expression here. So this will be equal to the limit as a approaches 0 plus of the integral from a to 1 of 1 over the square root of x times x plus 1 dx. And then we add to that the limit as, now we'll use b approaches infinity of the integral from 1 to b of 1 over square root of x plus 1 dx. And we see that those integrals have the same integrand, so let's just handle that integral on its own, take care of the limits later. So the integral of 1 over the square root of x times x plus 1 dx is what we have to solve. How are we going to do that? So I'll give you a hint. It's not easy. And I highly, highly encourage you to solve this on your own. Pause this video, take the time to solve it on your own, do whatever you can, use any method that you want, and then I'll show you the way that I solved this. So hopefully you've paused and done that. The way we're going to solve this, which may be a surprise, is u substitution. Watch this. We're going to let u equal the square root of x. If you take the derivative of u, we're going to get 1 over 2 square root of x dx. Now, the way we're going to rewrite this integral is we're going to keep the square root of x in the denominator as is. We're not going to convert that to a u. So we'll leave that as square root of x. But in the parentheses where we see an x, we're going to replace that with u squared. Right? Because the square root of x squared is x plus 1, and then dx is now equal to 2 times the square root of x du. And now we see that these square root of x's cancel. Isn't that beautiful? This gives us 2 times the integral, I shouldn't be using black here, 2 times the integral 1 over u squared plus 1 du. Gorgeous. So this is going to equal 2 times arctangent of u, but u we said was the square root of x, so we'll just replace that with the square root of x. So there you go, that's how you solve that integral. It's insane, but it's really cool. Okay, so we've solved that integral, now we have to take care of our limits. So returning back to what we had in black, this is the limit as a approaches 0 plus of 2 times arctangent of the square root of x, evaluated from 1 down to a, plus the limit as b approaches infinity of 2 times arctangent of the square root of x, evaluated from b down to 1. Fundamental theorem of calculus this. Limit a goes to 0 plus of 2 arctangent Square root of 1 is just 1. And then we subtract from that 2 arctangent the square root of a. We add to that the limit as b approaches infinity of 2 arctangent of the square root of b minus 2 arctangent square root of 1, which is just 1. So we're left with 2 arctangent of 1 minus 2 arctangent. We can plug in 0 plus for a, and we get basically square root of 0 here. Plus, we can plug in infinity for b. We get 2 times arctangent of the square root of infinity, which would just be 2 arctangent of infinity. And we subtract from that 2 arctangent of 1. We see the first and last terms cancel. So we're left with 2 arctangent of infinity minus 2 arctangent of 0. Both of these we've seen multiple times throughout this video. So this will be 2 times arctangent of infinity is pi over 2. And arctangent of 0 is 0. So we're left with 2 times pi over 2, which is equal to pi. And there we go. That's our solution. So again, we can see that these integrals are just continuously getting more complex, but we have all of the tools to solve them. It's just knowing when to apply those tools. So do not be afraid to split apart your integral if that makes it easier. I know solving 2 integrals is less fun than solving 1 sometimes. I mean, I kind of like solving integrals, so I'm happy with solving 2. But like, this just seems like a lot more work. But hey, it saves so much more time and confusion than having to handle 2 limits simultaneously with this. So that's the main tip from this one. There you go, improper integrals. I hope you learned a lot. This is a really interesting section, I think. So hopefully this was educational. And yeah, hopefully you're feeling more confident with yourself with integrals. And yeah, as always, take care and see you in the next video.